Listen closely, Neet aspirants. Today, we are mastering dimensional analysis, which is basically the grammar check of the physical universe. Every physical quantity can be broken down into base dimensions, represented by square brackets. Take force, for example. Force is mass times acceleration. So, its dimensional formula becomes mLt to the power of -2. Now, let us introduce the golden rule, the principle of homogeneity. Think of this principle as an exclusive club. You can only add or subtract physical quantities if they have the exact same dimensions. You cannot add velocity to force, just like you cannot add apples to oranges. Look at the famous equation of motion. X equals x0 plus v0t plus 1/2 at squared. If we break this down, the dimension of every single term is simply length, represented by L. Because every term matches, this equation is dimensionally correct. But beware of the NTA traps. Dimensional analysis has strict limitations. First, it is completely blind to dimensionless constants. It cannot tell the difference between 1/2 mv squared and 3/16 mv squared. Both are dimensionally correct, but only one is physically true. Second, it cannot tell apart different quantities with the exact same dimensions. For instance, work and torque both share the exact same formula, mL squared t to the power of -2. Finally, the arguments of trig, log and exponential functions must always be completely dimensionless. Memorize these limitations and secure your +4 marks.
Let us tackle question 1. A classic theoretical concept checker directly testing the limitations of dimensional analysis. The question asks you to choose the correct statement regarding dimensionally correct and incorrect equations. Let us run the concept check. Remember our major trap rule. Dimensional analysis is completely blind to numbers and constants. Take a look at case A. The formula k equals 1/2 mv squared. This equation is dimensionally correct, and it is actually correct in physics. This proves that a dimensionally correct equation may be actually correct, validating statement 2. But look at case B. What if I write k equals 3/16 mv squared? This equation is also dimensionally correct, but it is physically completely wrong. This proves statement 1. A dimensionally correct equation need not be actually correct. Because both statements 1 and 2 represent true physical limitations, option 4 is the correct answer. Secure those +4 marks. Moving to question 2. This is a brilliant mock paper concept that tests the dimensionality constraint of arguments. The question gives us a wave equation, y equals a sine of aet minus bvx. It asks for the dimensional formula of the ratio a over b. Here is the NTA limitation rule we learned. The argument of any trigonometric function must be entirely dimensionless. This means the term AET has no dimensions. So the dimension of A equals 1 over the dimensions of energy times time. Energy is mL squared t minus 2. Time is t. Calculating this gives us m minus 1 L minus 2 t1 for A. Similarly, the term BBX is also dimensionless. The dimension of B equals 1 over the dimensions of velocity times distance. Velocity is L t minus 1. Distance is L. This gives us L minus 2 t1 for B. Now simply divide A by B. Notice how the L minus 2 and t1 terms cancel out perfectly between the numerator and denominator. We are left with exactly m minus 1 L0 t0. Match this with our choices and option 3 is correct. Mark it and let us move on. Question 3 presents a classic NTA profile, the printing error question. It looks scary, but it is just a double test of the homogeneity principle. We are given a corrupted relativistic mass equation and asked to find the dimensions of eta 0 and b. Let us break it down into 2 steps. Step 1, look at the denominator. We see the term 1 minus b over c squared. By the subtraction rule, you can only subtract quantities with identical dimensions. Since the number 1 is totally dimensionless, the fraction b over c squared must also be dimensional. Therefore, the dimension of b must exactly equal the dimension of c squared. The speed of light c is L t minus 1. Squaring that gives us L squared t minus 2 for b. Now step 2. Because the entire denominator is dimensionless, the dimensions on the left hand side must equal the numerator on the right hand side. So the dimension of mass m equals the dimension of eta 0 squared. Taking the square root of both sides gives us m to the power of 1/2 for eta 0. Match these two results with the choices and option 4 is your perfect answer. Question 4 tests the third major limitation of dimensional analysis, the indistinguishability limit.
The question gives us the radiation energy formula, E equals hf. It asks us to find which quantity shares the exact same dimensions as Planck's constant, h. First, let us find our target. Rearranging the formula, h equals energy over frequency. Energy is ml squared t minus 2. Frequency is t minus 1. When we divide them, we get the dimensional formula for Planck's constant, ml squared t minus 1. Now, let us test the options. Option 1 is angular momentum. The formula is moment of inertia times angular velocity. That is ml squared multiplied by t minus 1. This gives us exactly ml squared t minus 1. It is a perfect match. But wait, check option 2, angular impulse. The formula is torque multiplied by time. Torque is ml squared t minus 2 multiplied by time t. This also gives us exactly ml squared t minus 1. Another perfect match. Because dimensional analysis cannot distinguish between these entirely different physical quantities, both share the exact same formula. Therefore, option 3 is your correct choice.
Question 5. This is perhaps the most famous application of the homogeneity principle in the entire NTA syllabus, the real gas van der Waals equation. We are given P plus A over V squared multiplied by V minus B equals RT. The question asks for the dimensional formula of the constant A. Apply the homogeneity addition rule. Look closely at the first bracket. The term A over V squared is being added directly to pressure P. This is only mathematically allowed in physics if both terms share the exact same dimensions. So the dimension of pressure must exactly equal the dimension of A over V squared. Rearranging this, the dimension of A equals the dimension of pressure times the dimension of volume squared. Let us plug in our base dimensions. Pressure is force over area, which gives m L minus 1 T minus 2. Volume is L cubed, so squaring it gives L to the power of 6. Multiply them together. The L terms combine. Negative 1 plus 6 is exactly 5. This gives us our final answer, m L5 T minus 2. Option 1 is a perfect match. Lock it in. Visit neetapp.in or download Neet app for more chapter-wise or concept-wise MCQ solving.